So this is a talk on astrophotography. If you're interested in photographing the night sky, this is how to do it without shelling out huge amounts of dosh. In other words, photographing without ridiculously expensive equipment. That's the idea. So if you wanted to take photographs of the night sky, what do you need? Well, the best way is to start simple, and then I can tell you a little bit about telescopes and cameras and so-called star trackers. I'll explain what those are just shortly. And then I'll be showing some of the images, some of my images, to give you an idea of what you can do with minimal equipment. And then I'll say something about what you can do if you are lucky enough to go somewhere with really dark skies. That doesn't include Liverpool. So firstly, starting simple, just a camera on a tripod. If you've got a camera, stick it on a tripod with nothing else. You can point it at the sky, open the shutter. You have to figure out how to control your camera, so you'll need perhaps to read the manual. If you expose for, in this case, 5 minutes, and this is pointing north, so there's the pole star that has hardly moved at all in 5 minutes, and notice all the other stars are little streaks, because in 5 minutes the Earth will have rotated a little bit, and hence the stars will appear to have moved. If you expose for longer, you get much longer streaks as the stars appear to circle Polaris. So here, for instance, a 6-hour exposure, not one long 6-hour exposure. With digital cameras, you can often take lots of short exposures and then add them together. There's software that will help you do that if you've never done it before. So in this particular case, I just took lots and lots and lots of 1-minute exposures. Each one, the star has trailed a little bit, and I've added them all together to give this effect of the stars circling around Polaris. You can perhaps tell it's a 6-hour exposure because if you look at these arcs, they are approximately 1/4 of a circle, because of course the Earth rotates 1/4 of a rotation in 6 hours. And software will allow you not only to add all the images together to give star trails, it also gives you the option of making a movie, so that because you're taking lots and lots of short exposures, you can add them together and start accumulating the data so that you get this effect again of the Earth's rotation as the stars wheel their way around Polaris. As you can perhaps tell from the foreground, this particular shot was taken from an observatory site, but it works equally well from your back garden, as long as you can see a reasonable chunk of sky, a wide-angle lens, no other equipment necessary to get these sorts of star trails. If you're lucky enough, a comet might come by. They do every once in a while, a few times a year, a comet comes by. This particular one was large enough to be easily caught with a camera on a tripod. Again, no other equipment necessary, no telescopes, just a camera on a tripod taking, in this case, a 30-second exposure. This is Comet Holmes, where the nucleus of the comet has this large diffuse coma around it. If you're lucky enough, you don't tend to get aurora like that from the UK. I know there have been a few in the last month or so, but these were taken in Iceland, where it's not just a little bit of a green glow on the northern horizons you see. When you get the full northern lights in Iceland, or I guess Scandinavia or Alaska as well, it basically lights up the entire sky. So you get beautiful auroral curtains visible. In this particular case, there's the constellation of Orion, for those who know their way around the sky, and there's the Pleiades, the Seven Sisters, that are just about visible through the aurora. So if you really want to catch these, you can either sit in the UK and wait, but you might have to wait a long time, or you try to go as far north as possible to catch the northern lights. And I can recommend either Scandinavia or Iceland, or perhaps parts of Canada. Strictly speaking, not the night sky, but again, in terms of having to be in the right place at the right time, it is spectacular to catch a total eclipse of the sun, where the disk of the moon just covers the disk of the sun, blocking out most of the light from the sun and revealing the wonderful, exquisite structure of the solar corona. This particular picture was taken in an eclipse some years ago now, back in 2006, where some friends and I went where we thought there was most likely not to be cloud, so we went to the Sahara Desert. That's not known for its rainy environment, so that we figured would be the best. So what about telescopes? Well, I said without ridiculously expensive equipment, but of course you can, if you wish, spend enormous amounts of money on telescopes if you really want to. For instance, the Hubble Space Telescope has been operational for more than 30 years now. It's not long before it's going to be pensioned off, so keep your eyes on eBay because it will be turning up sooner or later. But even so, you'll probably need a fair bit. Even the second-hand value will be quite high, and not that many people have got a few $1 billion to spare to be able to take the sort of pictures that I'm sure you're used to in magazines and as you've seen on TV. But amateurs, of course, have an enormous number of telescopes available to them in terms of purchase, but unfortunately, none of them are particularly cheap. If any of you are seriously thinking about buying a telescope for yourself or a young one, then I can give you some advice as to the sort of telescopes you ought to be looking at. But generally speaking, most amateur telescopes would start at a few £100 and they go through thousands of pounds, and if you'll excuse the cliche, the sky's the limit in terms of what you might want to pay for a telescope. But bear in mind that you don't need to think about a telescope if you're interested in photographing the night sky. That's one way of doing it, and if you have got a telescope, then you can get some glorious views of the moon. I'm not sure what it's going to be like tonight. We have a crescent moon, and it might be possible to actually catch a glance of the craters on the moon if you go up there a little later. But it can be fascinating. I know it's to some extent rather mundane, it's just the moon, but even so, if you look at the moon night after night and you see the way the shadows change, the shadows in the craters, the shadows on the mountains, it can be quite fascinating just looking at our own nearest neighbor. And then, of course, you've got the other possibilities of things like the planets. That's a rather old picture. This was taken about 20 years ago when I first got a telescope, just to prove to myself it is possible to capture an image of these distant planets. And although it's not the sharpest picture you're ever likely to see of Saturn, we get spoiled by the idea of these spacecraft visiting the outer planets. But the fact that from your back garden you can get a picture of Saturn, and you can see the fact that it's made of more than one ring, there is a division between the rings, and you can see the shadow of the planet that's cast onto the rings behind it. So from your back garden, you can get some nice images, but you don't need to think about telescopes if you're only interested in photographing the night sky. There are cheaper ways of doing it. So I've mentioned telescope, and strictly speaking, no, you don't need a telescope. So this is a different way of photographing the night sky without the idea of the stars trailing. Remember, the Earth's rotation means that if you don't do anything, the stars will appear to move in the sky, and any long exposure you take will have the stars moving. But there is a way of dealing with that via a device called a star tracker. Here's one I built myself. It's basically just a means by which, if the Earth is rotating, you want the camera to rotate in the opposite direction and hence stay static relative to the stars. You can build one of these trackers for yourself. I've got instructions over here. If anybody wants to try it as a DIY project, you can build yourself a tracker. This is one I built quite a few years ago. And there are lots of commercial variations on a star tracker as well. This happens to be the one made by a firm called Ioptron. There's at least, I don't know, half a dozen other variations from different manufacturers who will sell you a star tracker if you're interested. They are not very large. You can see the size here when you think of the cameras that are bolted onto the front. Basically, all that's happening is that inside there's a motor which turns this little platform, which is where you mount the camera. It turns that platform at one rotation per day in the opposite direction to the Earth's rotation, and hence effectively keeps the camera still, as long as you make sure it's lined up in the correct direction, which is why there's a little polar scope here to make sure you're lined up with Polaris to make sure that you've got your axis of rotation lined up with the Earth's rotation. So that's what's inside these things. They're relatively simple. They're basically a motor in a box. So usually battery driven, a little bit of circuitry which feeds a motor and a gearbox, and then a worm gear, which then ultimately turns this large disc, which is connected to your camera, at one revolution per day. And hence you're then able to take pictures of the sky, and even long exposures hopefully will not show the trailing that you would get with a static camera on a tripod. So let me show you the sort of things you can do. If you've already got a camera, it could be a mirrorless camera, it could be a digital SLR camera, it could be a bridge camera. If you've already got a camera that you use for taking daylight pictures, they work fantastically well at taking pictures of the night sky as well. So let me show you what you can do. This is using the camera that I use for daylight photography. I'm quite interested in wildlife photography. I like taking pictures of lions and zebras if I ever go on safari. And using that same camera that is used for daylight photography, I also use that on a tracker to take pictures of the night sky. And these are all pictures taken with my digital SLR camera of various things that I've seen in the night sky. Notice a lot of them are actually quite colourful. You don't tend to notice this when you look at objects in the sky. Even if you look through a telescope, you don't seem to see an awful lot of colour. That's simply because your eyes, the colour receptors in your eyes, don't work particularly well at low light levels. And so the camera can pick up the colours. These are natural colours. These are not false colours. In many cases, they've been enhanced with a little bit of extra contrast to make those colours pop, but these are genuinely the colours of these objects. This particular cloud of hydrogen does indeed glow slightly pinky red. This particular cloud is indeed either blue or slightly lilac coloured. This over here is orange and blue. The Milky Way tends to be a relatively boring beigey sort of colour, but we'll see in a bit more detail this supernova remnant here, this star that blew itself to pieces more than 10,000 years ago, tends to have a lot of red and a lot of blue. So all of these colours are real, and all of them can be brought out through this idea of putting a camera on a tracker. Is that a question at the back, or are you just half raising a hand? Okay, fine. So my point is that yes, if you are interested in astrophotography, then you can invest in a telescope if you wish, and you can get some absolutely superb images. You might have seen some amateur pictures taken and published in magazines like Astronomy Now or Sky at Night magazine, and you can get some fantastic images with astrophotography through a telescope. But bear in mind, it will take a certain amount of time to build up the expertise needed to take images with a telescope. It'll take time, it'll take effort, and perhaps more importantly, it'll take cash. It is not the cheapest of hobbies to buy a telescope that's suitable for doing astrophotography of very distant galaxies, for instance. When you take images of the night sky, bear in mind the first thing you see on the back of the camera might be a little bit disappointing. Because, for instance, if I point my camera at the sky and take a picture of this nebula is called the North American Nebula, for reasons you might be able to glean from the outline on the right-hand side. But the left-hand side shows you the raw image. This is what you might see on the back of the camera if you point it at the sky and take a picture. More than likely, you will only just make out the object that's of interest to you, and a lot of what you're looking at is light pollution, sky glow, because unless you are in the darkest part of the world, sitting on top of a volcano in the Canary Islands or Hawaii or the top of the Andes in Chile, the chances are you will suffer from some streetlights being not too far away, and hence you will get a whole load of orange, or at least you will not get a nice dark black sky in the background. But that doesn't matter too much, because these days software is so good, you can take your digital image and you can find lots of software tools, lots of apps if you prefer, that will allow you to take your raw image and process it in such a way that you make the sky a little bit darker and you bring out all of the detail that's in this particular case, this nebula, which is made of hydrogen and oxygen and is glowing a little bit red and a little bit blue. So all of the information on the right is buried inside the image on the left. It's just difficult to see, and you need a little bit of help with software in order to bring out these interesting images. So that's one thing to bear in mind. If you ever try this yourself, don't be disappointed by the fact that your first attempt doesn't look very spectacular. All images look like that. Okay, perhaps not Hubble images, but basically all images to some extent will suffer from some light pollution, and it will take a little bit of tweaking to get it to the point where you get the sort of image that you would like to see. So this is one of the images I showed earlier. It's called the Rosette Nebula, and it's basically a sort of stellar nursery. There are stars being born. Those few stars you can see in the center are probably relatively young stars that are born out of this hydrogen cloud. You can see a little variation in color. The color on the inside isn't quite the same as the color on the outside. Most of these colors are relatively natural in the sense that if your eyes were sensitive enough and if you stood in front of this nebula, you would see it glowing faintly at the pink end of at the red end of the spectrum. This is a picture I took many years ago, and so its quality is not quite as good as the more recent ones, but I thought this was quite interesting because it shows what would happen at the end of the sun's life. Once the sun has run out of fuel, it'll expand as a red giant, and then it will shrug off those outer layers, and the outer part of the star will end up as this so-called planetary nebula. Nothing to do with planets per se, but a load of gas that's been shrugged off from the outer part of the star. So in a sense, we're looking at the future of our own sun. And I thought it was interesting not to claim that this is the world's best astrophoto, which I'm sure you agree is not, but I thought it was interesting to compare it with a Hubble Space Telescope image. I've tried to show them roughly to the same scale. My picture is a much wider field of view. The Hubble Space Telescope is a much narrower field of view. The colors are not so different, and of course the Hubble shows more detail, but remember, the amount of satisfaction you get from taking your own images. You're not trying to do better than the Hubble or the James Webb Space Telescope. Nobody can do as well as those telescopes. But to be able to take a picture in your own back garden and say, there's a star that basically blew itself to pieces, and that's ultimately what's going to happen to our sun. Yes, it's not as good as the Hubble image, but that was taken with my camera, and that was taken with something that costs billions and billions of dollars. Well, mainly your taxpayers' money. Remember, the Hubble Space Telescope was built by NASA and ESA, the European Space Agency, so you have contributed to the Hubble Space Telescope. So in a sense, that's your picture, and that's mine. And yes, one is distinctly better than the other, but think about the price difference. And it doesn't matter how bad the individual image is, to take it yourself gives you enormous satisfaction. This is a star that went supernova a long time ago. I can't remember exactly how long, at least 10,000 years ago. So a star that used to be somewhere in the middle there blew up and produced this shell of material, basically the remnants of this particular star. Just like a soap bubble, if you make a soap bubble that's spherical, you don't tend to see the entire sphere. You tend to see the edges where you're looking through most material. And so this might be a large spherical bubble, but you tend to see the edges most prominently. These are effectively shock waves as the material moves out into the interstellar medium, the medium between the stars. And this image was taken, let me remind myself, yes, this is a series of 1-minute exposures, and this particular image was taken from outside my front door, a few meters away from an LED street light. So even if you have light pollution, even if you have street lights fairly close to your garden, you can still do astrophotography. A combination of using filters to try and limit the amount of sky pollution, plus the software that allows you to process the image and bring out the details of the nebula, even though there's an LED street light trying to shine into your camera and spoil your image, it is still possible to do astrophotography with a tracker and with your camera, even if you live in a suburban area with streetlights very close. So don't give up on the idea of taking pictures for yourself. Don't just say, oh, well, I'd love to take pictures, but I live in the city, so it's never going to work. It can work. If we move out from our own Milky Way and look at what else is going on, this is in a sense, our immediate neighbor. This is the Andromeda Galaxy. Same camera taken with a telephoto lens, and again a series of 1-minute exposures all added together with the camera sitting on a tracker to try and minimize the effect of the Earth's rotation trying to trail the stars. So we can see a lot of detail in the Andromeda Galaxy. We can see these darker lines, these so-called dust lanes, giving us an idea of the structure of the Andromeda Galaxy, similar in many senses to the structure of our own Milky Way galaxy, a spiral galaxy. And notice that it has a couple of small companions as well. These are small satellite galaxies which are, as it were, buzzing around the Andromeda Galaxy. We can't see them move, but we think that the motion of these are such that they are orbiting the Andromeda Galaxy, much like some small galaxies are orbiting the Milky Way galaxy. This is 2.5 million light years away. In other words, we're looking at an object where the light left the object 2.5 million years ago. And during those 2.5 million years, the light has been traveling from the Andromeda Galaxy until it arrived on the day I took this picture. But this is by no means the most distant object that you can photograph. During lockdown, We were told always to look at the ground and being told to keep our distance 2 meters from somebody else. But Stephen Hawking said, don't look down at your feet, look up at the stars. And I thought, that's a great message. So during lockdown, I set myself the challenge. How far can you see with the camera? This is about as far as you can see with the naked eye. When you look into the sky, you can't see more than about 2.5 million light years. That's the most distant object you can catch without any optical aid like binoculars or telescopes. But if you've just got a camera and a tracker and a back garden, what is the most distant object you could possibly catch? So I did a little bit of research by looking up a paper of various distant objects. These distant objects, we don't have to worry too much about the astrophysics, but they're called quasars. They are galaxies with very bright central nuclei. And I thought, is it possible to catch one of these with a camera sitting on my star tracker? Because that sounds like exactly what Stephen Hawking was talking about. Look up, don't look down at your feet. So I pointed the camera at a patch of sky where I expected to find this particular quasar, because I looked up what its coordinates were and figured out it's not that bright object in the middle. That just happens to be a star which is bright enough that I can easily catch it, and I know that the quasar ought to be just next door to that. So I put my camera on this tracker, took it outside, put it next to the wheelie bin, tried to avoid the street light if possible. In other words, put the wheelie bin such that it cast a shadow so that the LED street light didn't pour straight into my camera, and then I exposed for as long as possible. It was the middle of the summer, and of course we don't have an awful lot of night during the summer, but I exposed for as long as possible and then took the original image, which is a few degrees square, and zoomed in to where I expected the quasar to be. The quasar is the least impressive object in this picture because that is it. It is a tiny, tiny, tiny little dot. And even if I were to blow it up, it still doesn't look particularly spectacular. But most of the light from this quasar, this nucleus of a very remote galaxy, if we blow it up, you can see that most of the light is hitting just 1 pixel of the camera. The camera has got 20 million pixels in it, and the quasar, the light from the quasar, arrived in basically just 1 pixel. But the incredible thing about this image is not how photogenic it is. It's the worst case. It's just a little blob. But if we think about how far the light has traveled, this particular object is on the other side of the observable universe. It is extremely remote. Its distance now is some 25 billion, not million, 25 billion light years. It's not a question of how many million years have the light been traveling. The light has been traveling for 12 billion years to reach me. In other words, the light left this particular object long, 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 long before the Earth even existed. We're not talking about going back to the dinosaurs. We're talking about going back to the point where the sun and the Earth didn't even exist. So the light has been traveling for something like 90% of the age of the universe. And when it finally arrived on the Wirral, in between the clouds, it finally hit my camera sensor, despite having traveled for 12 billion years. It was a slightly cloudy night, but eventually the clouds parted and the light produced that image. And to realize that you can, using the technology that exists for taking a picture of your cat or your family or a tree, the same technology, the same camera that you use to take daylight pictures can capture light that's been traveling for most of the age of the universe and at a distance of 25 billion light years. Even more remarkably, how fast is this thing receding from us? The universe is expanding. So very distant objects are moving away from us. The distance to those objects is getting larger and larger and larger, second by second, day by day. And the recession speed, the speed at which this galaxy is moving away from us, is twice the speed of light, because it is so distant and the universe is expanding. Objects that are close to us recede at a small velocity. Objects that are much further away recede much faster. This one is so distant, it's receding at twice the speed of light. And it takes a little bit of figuring out how on earth can the light reach us? If this object is moving away from us at twice the speed of light, and the light can only travel at the speed of light, how on earth can that light ever reach us? And this was a little bit of a paradox, and I had to sit down with pencil and paper and take a while to figure out how that actually works. But even more remarkable is the fact that technology today, digital cameras and a simple little star tracker, which might cost you 10 or 20 quid to build, enable you to take pictures like this. So I'm indebted to Stephen Hawking for suggesting I try and take a picture of the most distant object possible. Let me finish by just saying that although you have to contend with light pollution if you stay in the UK, especially if you live in the middle of Liverpool, there are options. Maybe you're lucky enough to take holidays in other places in the world where you don't have to fight against light pollution. If possible, I like to go on a holiday with friends to various parts of East Africa where you can get away from streetlights. You can get hundreds of miles away from the nearest streetlight. So I like looking at wildlife. I take binoculars with me to watch wildlife. I like photographing wildlife. I take binoculars that also are used at night for astronomy. And if I take a camera with me anyway, it's very little additional to my luggage to say, let's take a tracker as well, which allows me then to do astrophotography. So a safari basically includes all of those three interests of mine. Animals by day, stars by night, in which case sleep when you get home. There's no point in wasting a good holiday by sleeping when you could be photographing lions during the day and photographing stars at night. From the UK, it's sometimes difficult to make out the Milky Way, unless you are lucky enough to live in the middle of Wales or the very northwest of Scotland, where you can get away from streetlights. So from England, you can just about make out the rather hazy view of the Milky Way. But if you're lucky enough to go somewhere like Africa, then the Milky Way is really bright. And you can see with the naked eye, not only the bright patches of the Milky Way, you can see all the dark areas, the dust lanes, all of the structure that exists within the Milky Way, because we're looking at so much structure between us and the center of our own galaxy. And of course, as soon as you do astrophotography, then you start to be able to see the colors that are difficult to see with the naked eye, because your eyes simply do not work well in color under low light conditions. So this is what the Milky Way looks like from a very dark site. It's very difficult to get that sort of image if you've got a huge amount of light pollution. But if you were to get away from Liverpool, somewhere out into the country, and you've got a tracker, then it's possible to take images like that. I guess some of you might understand some of these patterns, these constellations. This is the constellation of the Scorpius, this S shape with a sting in the tail down here, and the claws of the scorpion up there. The very bright object there is Jupiter, and it's not obvious, but that is also a planet over on the left-hand side. That's Saturn. This was taken a few years ago, before Saturn and Jupiter changed their relative position in the sky. So perhaps the take-home message is a tracker, not necessarily this one, but a tracker similar to that one, or a homemade tracker. It might weigh less than a kilogram. It's relatively compact. It's an easy sort of thing to put in your luggage. If you're ever going anywhere on holiday where you stand a chance of getting away from streetlights, then if you're taking a camera with you anyway, why not take a tracker, and then you can take astrophotos similar to the ones I've been showing you for the last half hour or so. Thank you for listening.